before thinking about fluid flow, here's an example of a problem involving the buoyant force. You've got a hippopotamus at the bottom of the river, just walking along the bed of the river, and the mass of the hippo is 1,500 kilograms, and the density is 1,030 kilograms per cubic meter. And what we'd like to do is figure out how strong the force is, the force from the riverbed pushing up on the hippo. That's a normal force from the riverbed pushing up on the hippo. So the way we approach it is the same way you approach all those problems that you were working on Monday. First, figure out what forces there are, and then figure out how they combine to give you a net force. So in this case, there's of course the hippo's weight pulling down, the normal force from the bed of the river pushing up, and also a buoyant force pushing up because the hippo is surrounded by water. Next, you write down the algebraic expression that shows how those forces combine to give you the net force. And we'll just take all the force in the positive direction minus all the force in the negative direction. We'll say up is the positive direction. So all the force in the positive upward direction is the buoyant force and the normal force. And all the force in the negative direction is the weight. Those are the three forces, and they combine this way in order to give you the net force. Net force is equal to mass times acceleration. But this is net force along the vertical dimension. And the hippo is not moving vertically. Or to put it another way, the vertical velocity of the hippo is constantly zero. And any constant velocity means no acceleration. So the vertical acceleration is zero, the vertical net force is zero. So now we have to figure out the value of this number. We can figure out this number, and we can figure out this number. In order to figure out this number, there's something else that we have to figure out first, because remember, buoyant force is the weight of the water that was displaced, the weight of the water displaced by the hippo in this case. So to do that, we have to figure out the volume of water displaced, which is the same as the volume of the hippo, because it's the hippo that's displacing the water. So the volume of the hippo is mass divided by density, because remember, density is just mass divided by volume. So there's the mass of the hippo, 1,500 kilograms, divided by density, 1,030 kilograms per cubic meter, and that comes out to 1.456 cubic meters. Really more, 1.456 cubic meters. Now we can figure out the size of the buoyant force on the hippo. Remember, the buoyant force is the weight of water displaced. Weight is just mass times g. So the buoyant force is mass of the water displaced times g. In all of these fluid problems, we always want to write mass as density times volume. So mass of the water displaced is just the density of water times the volume that was displaced by the hippo. And the volume of regular fresh water is about 1,000 kilograms per cubic meter, 10 to the third kilograms per cubic meter, times the volume that gets displaced. Well, the volume that does the displacing is the volume of the hippo. So 1.456 cubic meters of water are displaced by 1.456 cubic meters of hippo. And that's density, volume times g. Density, volume times g, and when you multiply it together, you get 14,267 newtons. Then, now we know this number, And it's easy to figure out this number. Weight is just mass times g, mass of the hippo times g, which is 1,500 kilograms times g. And that comes out to 14,000. Let me make sure I've got the numbers right. Comes out to 14,700 newtons. So we know this number, 14,269. N, we're trying to figure out, we don't know it yet, minus the weight, which is 14,700 newtons. That's the net force, which is the net vertical force, which is 0 in this case. So 14,269 minus 14,700, that's minus 431 newtons. Equals 0. So the normal force from the bottom of the river pushing up on the hippo is 430 newtons, or about 430 newtons, rounded off to 2 digits, since in some of the numbers that we put into the calculations, we have only 2 significant digits. So we're allowed only 2 significant digits in our answer. So, see what I did there? I did not start by looking for an equation that had the normal force in it. I started by just identifying what forces are there in the first place, and then use that to write down the way those forces combine. Some algebraic expression that shows how those forces combine to produce the net force. And then I can put in the numbers. All right, now let me move to the other blackboard for a discussion of fluid flow. And we, in our model, our simplified model for understanding flowing fluids, we'll consider an incompressible fluid. And incompressible means just what it sounds like. You cannot, an incompressible fluid, like water for instance, like most liquids, cannot be squeezed into a smaller volume. That is, any given mass of incompressible fluid takes up a certain amount of volume, and you cannot take that mass and squeeze it down into a smaller volume. Well, in other words, any mass of incompressible fluid has just one volume that it fits into. You can't squeeze it into a smaller volume. Any one particular mass has the same volume all the time. That means constant, uniform density. Everywhere in the path of the flowing fluid, whatever else might be changing, fluid density does not change if it's an incompressible fluid. And one consequence of constant density is that the so-called volume flow rate is uniform, constant, the same in every point in the path of the fluid. The definition of volume flow rate is this. Use capital Q for a volume flow rate. and it's just the volume of liquid flowing past some point in this much time. This is the amount of time it takes for this much of a volume of liquid to flow past any one particular point. And constant density means this is uniform. It's the same everywhere. And we can see why this fact means that this is going to be uniform everywhere in the path of the fluid. Think about what would happen if Q could be different at different points in the fluid, if the flow rate were different at different places. Here's our example. Say fluid is flowing from left to right, and at point 1 there's a certain flow rate, some number of gallons per second, and at point 2 there's a smaller rate of flow, fewer gallons per second, which means if this were true, can't be true, but imagine what would happen if it were true, then there would be more gallons flowing in to this space than flowing out of this space. More gallons of fluid flowing into this volume than flowing out of this volume, because Q2, right, the number of volumes per second flowing past point 2, that's the flow out of this volume. Q1, the number of gallons per second passing by point 1, that's the flow into this volume. So there's more gallons flowing in than flow out. That means more and more fluid would pile up in this volume. Well, this volume stays the same, but then you have more and more fluid piling up in there. That means there's more mass, more and more mass, more and more mass piling up in this same volume. If this were true, then the density of the fluid between point 1 and point 2 increases. But that can't happen because in an incompressible fluid, the density stays constant. So it cannot be the case that that one flow rate and flow rate at another location are different. If it were different, then you'd have different densities at different points, and that doesn't happen for an incompressible fluid, and most liquids are incompressible. Okay, let's think a little bit more about volume flow rate. Imagine some fluid flowing through this tube and flowing this way. Velocity is pointing in that direction, and here's the speed, and this volume of fluid is passing by. And we can write this volume of fluid as a product of two factors. The length, call it L, and then the area, which is just the cross-sectional area of the tube. Right? Take a slice of the tube perpendicular to the tube, and the area of that slice is the area through which the fluid has to pass, or it's the area on this dimension of the fluid. So imagine that in delta t seconds, this is the volume of fluid that passes by this point. For all, that means that delta t has to be long enough for all the fluid at this end to make it all the way across this far in delta t seconds. So the flow rate, the volume that flows by, is just area times length divided by delta t, but delta t is the length of time it takes all this part of the volume here at the left-hand end to make it all the way across by a distance L. So the distance that's traveled in delta t seconds, distance traveled divided by the length of time it takes to travel that distance, that's a speed or magnitude of velocity. So our conclusion is that the volume flow rate, you can write it as either volume per second, gallons per second passing by any point, but another way of thinking about volume flow rate is just speed times the area through which that fluid is passing. And if the volume flow rate is the same at every location in the path of the fluid, then this product is the same at every location in the path of the fluid. And to say that this is uniform, the same at every point, you could write it like that. V times A at point 1 equals V times A at any second point. That's what we call the equation of continuity, or at least the book calls it the equation of continuity. And an important conclusion that we can draw from that, imagine that the fluid flows through some narrow spaces and then flows through some wide spaces. Let's say fluid is flowing from left to right, and the narrow space we'll call 1, and then the wide space is out here. Of course, the cross-sectional area through which the fluid flows in at point 2 is much bigger than the cross-sectional area through which the fluid flows at point 1. So A2 is greater than A1. This factor is bigger than this factor. So in order to keep this product equal to this product, if this number is larger than this, then this number has to be smaller than this. So bigger area at point 2 means lower speed at point 2. Wider space means slower speed. Narrower space means faster speed. And you can see that if you look at the flow of a river. A big, wide river flows very slowly. You can hardly see the water moving. But if the river is flowing through some rapids, there are lots of rocks in the path of the water. So the water has to travel through narrow spaces between the rocks in order to move. And in that case, traveling through narrower spaces should have been area 1, sorry about that. Traveling through narrower spaces, an area that's less than it is elsewhere, traveling through narrower spaces, it moves at a higher speed. And that's basically because the volume flow rate is the same everywhere. imagine some volume of fluid, say this big. And for this whole bit of fluid to, say, get past this point, it's got to travel pretty quickly. But for that same volume of fluid to get past this point, right, that same volume of fluid, right, this volume, I think is, I mean this volume to be equal to this volume. For this volume to pass by point 2, it can move a lot more slowly. Here, the bit of the volume at the back is farther away from the front, so to get the whole volume through, it has to travel faster. Here, the back of the volume is very close to the front of the volume, so you don't need a high speed to get this whole volume past point 2 in time. Just to say a specific example of this, let's say these are circular tubes, and the radius here we'll just call R, and in this big circular tube, three times larger. The volume is 3 times larger. In that case, if we know what the speed at one point is, we can figure out the speed at the other point by just using proportionality. Say we know that the speed in volume 2 is, let's say, 1 meter per second. We can figure out what speed 1 is. How do we do that? Well, just rewrite this, divide both sides of the equation by A2, and we have, or divide both sides of the equation by A1, and now this becomes an equation V1 equals other stuff. So V1 is just equal to V2 times A2 divided by A1. And we know how A is related to the radius, just saying it's a circular tube, so the area is just pi times radius squared. Or to put it another way, this is constant, r squared is a variable, a is a variable. This is in the form of some variable equals constant times some other variable, direct proportionality, which means that when this number changes by some factor, this changes in exactly the same way by the same factor. If x doubles, y doubles. If x is cut down to 10% of what it was, y is cut down to 10% of what it was. And in this case, the two variables that are directly proportional are area and r squared, not r squared. Because this expression here means that everything in this term that isn't constant is the variable, and everything in this term that isn't constant is r times r, not just r. So area directly proportional to r squared. So in going from region 1 to region 2, how does r squared, we know how r changes. R gets 3 times bigger, but remember the proportionality is between area and R squared. How does R squared change? That tells us how area changes, because area is related to R squared, not just R. Well, square this whole equation and you see how R squared changes. The new R squared is 9 times the old R squared. The R squared in region 2 is 9 times the R squared in region 1. So if R squared increases by a factor of 9 when going from narrow to wide, then area increases by a factor of 9 when going from here to here, because area is proportional to R squared. Area will change exactly the same way as R squared when they are proportional. So R2 is 9 times bigger than R1. That means area 2 is 9 times bigger than area 1. Right? The radius is 3 times bigger, but the area is 9 times bigger. So A2 is 9 times bigger than A1, or A2 over A1 is 9. This ratio here is just 9. So V1 is just equal to V2 times the ratio of A2 to A1. A2 is 9 times bigger than A1. And then V2 was just 1 meter per second. So V1, the higher speed in the narrower region, must have been 9 meters per second. Meters per second. One other example, you have a homework problem that's a little bit like this. Imagine that you've got one tube, and the fluid that's flowing in there splits 3 ways into 3 tubes. But the areas of those tubes are all the same. Cross-sectional area here is same as this, same as this, same as this. So if we call this point 1, and we call this point 2, then here at this point, water is flowing through some area. Here at this point, all that water is flowing through 3 times as much area. Right? This is just as wide as this, but there are 3 of these tubes. So the total, the volume flowing past point 1 is the same, or the volume per second flowing past point 1 is the same as volumes per second flowing past point 2. But point 2 means you have to look at everything at this location, everything where water is passing through, and it's passing through in 3 separate paths, but all the same direction. So we have that, and then our continuity equation is that, but area 2 is 3 times bigger than area 1. So in order to keep these two things equal, this speed in the wider area has to be only 1/3 of V1's speed. Right, to say that algebraically, I can write V1A1 equals V2, and then write A2 this way, 3A1. And then cancel out the A1s, and we have V1 equals 3 times V2. Or V2 is just 1/3 of V1, as I said previously. V1 has the higher speed because the fluid has to flow faster to get the same number of gallons per second passing by this point as the number of gallons per second passing by this point, when there's 3 times more area for that volume to spread out. That's the continuity equation. And the other idea that we think about in fluid flow is Bernoulli's principle, and Bernoulli's principle is easily expressed in an equation that in some ways is similar kind of thinking to the continuity equation. So in Bernoulli's equation, we look at one point in one location in the path of some flowing fluid and measure a bunch of numbers and then combine them. Pressure at one point plus density of the fluid, g, acceleration due to gravity, times the elevation of that fluid, how high above the ground, plus 1/2 density square of the speed at that point. Bernoulli's principle tells us that this combination of things is uniform. This combination of the things is the same at every point. And in reading through section 5, you saw that was basically because of conservation of energy. So this combination of things at point 1 is the same as it is at any other second point. Pressure at that second point plus density g, elevation at that second point, plus 1/2 density squared the speed at that second point equals the same kind of sum at point 1. Now, the most interesting thing about Bernoulli's principle is seen most easily when we just imagine water flowing at the same elevation, right? Everything on the same level. The water isn't going uphill, it's not going downhill. In that case, in other words, if H1 is equal to H2, then this term is exactly the same as this term, and they just cancel out. H is the same here and here, so just subtract density GH from both sides of the equation, and what you are left with is a slightly simpler equation, and it's easier to see the interesting thing that's going on. Pressure 1 plus 1/2 density speed 1 squared equals pressure 2 plus 1/2 density speed 2 squared. Now let's imagine what happens again when water flows from a narrow place to a wide place. There's a certain speed here and a different speed there. The continuity equation tells us that where the area that the fluid has to get through is narrow, you get a higher speed. Where there's a wide area for the fluid to flow through, you get a slower speed. So in this case, V1 is greater than V2. Now look at Bernoulli's equation. V1 is bigger than V2, so this term here is bigger and this term here is smaller. In order to have this sum equal to this sum, where this number is big and this number is small, this has to be big And this has to be small. Small pressure making up for the fact that you've got a large value for this, and big pressure making up for the fact that you've got a small value of this. So that implies pressure 2 is greater than pressure 1. Wherever the fluid is flowing slower, that's a region of higher pressure. And really it flows slower because it's a region of higher pressure. Think of it this way. Look right here at the transition between the narrow and the wide part. Here the water was moving at a high speed, here the water is moving at a slow speed. So here in the transition, the water must have been slowing down. The water is moving this way. The velocity vector points that way. So if something is slowing down, that means there's a net force pushing backwards on it. And you get that net force pushing backwards because the pressure over here is different from the pressure over here. Right, the net force is just equal to the force pushing this water forward. Remember, pressure is force divided by area, so force is pressure times area. The force pushing forward is just this area times the pressure in this region. And then the force in the opposite direction is just the pressure times the area. And we're just considering water right here in the transition. So we're thinking of a very narrow range, a very thin region, so that the area here is really about the same as the area here. So I use the same value for A. If we use the same value for A, and we saw that pressure 2 is bigger than pressure 1, this force, the backwards pointing force from the pressure in region 2, is stronger than the forward pointing force caused by the pressure in region 1. There's a force pushing the water forward, but there's an even stronger force pushing the water backward because there's higher pressure in region 2. And that backward force is what made the water, change its velocity, slow down. It's going faster here. It got slowed down by the time it was here because in this region, it was feeling a backwards net force. And much more of this to come in class.